Alright, this video is a bad idea. Got here at 5:30. I recorded a whole video of it. No interruptions, no Rahul. I noticed about halfway through the video that this little stupid light stopped blinking. It's now 6:40, as you can tell. I'm going to try to record it again before class starts. But, you know, maybe it's just bad luck. Here we go. So, interval of convergence. Second last lesson in chapter 8. You shouldn't be doing this lesson until you've done 8.1, 8.2, 8.3, 8.4 with all of the assignments. Okay? You're probably watching this video in April if you're taking it slow. Maybe you're watching all the videos over spring break. I don't know. It's up to you. You're adults. Kind of. Not really. Radius of convergence of a power series is the distance from the center at which the series will converge. I think I would say at which the series will still converge, right? Because it will always converge at the center. Power series will always converge at the center. I'm going to write that down later. I had a perfect place to write it in the lesson. Oh, so perfect. The interval of convergence is the range of x values within which the series will converge. Will still converge. So, all as far as x can get. Now, let's specify this. Interval of convergence with ratio test. What did interval of convergence look like before? So we've seen IOC with power series. Lesson 7.4, lesson 7.5, etc., etc. 7.6, I think even. So we talked about the interval of convergence. So a power series looks like this, basically. With geometric. That's a key phrase. Other power series, you have to use this. A geometric power series looks like some constant times x minus c, here comes our whole, to the n. Now, this series, by the geometric series test, would converge when... Thank you for shutting the door so quietly, Rahul. See, he gets a shout out on the video, guys, because he didn't make a big interruption like 8.4. Anyway, so this series will converge when the absolute value of r is less than 1. That's what we call the geometric series test, right? What's r in this? In this series, r is the stuff to the n. We bust things out of the absolute value jail by doing this. We add c to both sides, or all three sides. Let's write it out for once. And we talked about how that would be the interval of convergence. And the radius was 1. Okay? That could change. Okay, guys? It's all very different. It depends on what's r. But that was the basic idea. We knew, because we know the geometric series test, we know these series will always converge as long as that radius, as long as that thing being exponentiated stays less than 1 in terms of its absolute value. The idea with the ratio test is that now we have a different criterion that's also easy to use for power series. Why is it easy to use for power series? Because power series always have exponentials. And if you look at the notes for 8.4, you will see that I say the ratio test is always useful for series with exponents. And a power series has exponents, so the ratio test is useful for power series. Hooray. Hopefully that all makes sense. I've said this like 3 times today already, and I'm very sad about it. I'm going to keep being sad. Sorry, everybody. All right. Find the interval of convergence and the radius of convergence of the following power series. So the key idea is to take the limit. We're going to take the limit, and then we're going to test the endpoints. Okay? The main thing I want you to think about is that unlike the geometric series test, the ratio test is inconclusive. If the limit of that thing equals 1. Okay? Alright? Just hold that thought in your head for a second. So the first step is to take the limit of the ratio. I want to see when is this limit add 1 to all the n's. Take all of the n's and replace them with n plus 1 is the more precise way of saying it. You want to be careful here. You got to be careful or else you don't eat. Okay, here we go. I want that limit for the ratio test. This has to converge. It converges when this is less than 1. So I want to find the values of x that will make this limit less than 1. Whoa, less than fun. Okay, so we're finding the values of x that will make this limit less than 1. So let's take this limit. A lot of stuff's going to cancel. That's what's nice about the ratio test. That n is hideous. 2, right, x, right, times n over n plus 1. I'm going to write it this way, which is very suggestive. Very, very suggestive. Because this part doesn't depend on n. So n increasing isn't changing that value. What's this limit? What's this limit? Highest power on top is 1. Highest power on the bottom is 1. The ratio of the coefficients, then 1 over 1. So we have, the question is, when will 2x be less than 1? You replace that equation with this, that's inequality, careful, with this inequality. Divide everything by 2. Okay, so this is my potential interval. So you have some idea of what's going on. That's my potential interval. I don't write it down yet. Don't circle it. Don't write it down. That's going to be a potential interval. So I took the limit. I wanted to see where it's less than 1. I finished the limit. Why don't I write limit here? Because I did all the stuff with n. There's no more n's. No more limit. I have a potential interval of convergence. I'm going to shrink this down. It's going to get pretty shrunk based on the first 2 trial runs I did of this lecture. This morning. At these 2 endpoints, when x is negative 1/2, when x is 1/2, the ratio test equals 1. The ratio test would have been inconclusive. So I'm going to write that down. RT inconclusive. The limit equal, oh, don't write limit equals, they'll do it. Limit, that guy, equals 1. Okay. So use other tests. We're going to use other tests. Other. Okay. So, we're going to check. Here's how it works in practice. Check. X equals negative 1/2. So I take x, and everywhere I see x in this series, I replace it to get this guy. 2 to the n, negative 1/2 to the n. They both have the same exponent, so I can simplify to be negative 1 to the n over n. Don't forget that n. This guy definitely looks like he's alternating. You may have seen him a bunch of times before. Doesn't matter. On the AP test, you still need to make these checks. You still need to make the checks, guys. So, what do I mean by checks? Limit n going to infinity of 1 over n, the absolute value, equals 0. And 1 over n decreasing. So this whole blue thing converges by AST. So the blue endpoint converged. The blue endpoint converged. The blue endpoint converged. More shrinky. I'm sorry. We're going to get kind of shrunk. I told you guys. I told you what would happen. I knew the future because I've done this 2 times. The other one you can't see anymore, but guess what? You have the power to rewind it. The other one we need to check. The other endpoint, we're going to check x equals positive 1/2, which would give me this series. 2 to the n times 1/2 to the n. Oh, that's not good too. Equals. We're going to be paranoid checking that blinking dot from now on. You could write it as 1 to the n, but 1 to the n, guys, is always going to be 1. Okay? And that, everyone should be screaming at the screen because it comes up so often, is a divergent harmonic series. So what did we show? We showed that the blue endpoint, negative 1/2, converged. The green endpoint did not converge. So when I go to write down the interval of convergence, IOC, I write down the 2 endpoints. This, negative 1/2. When x was negative 1/2, the series converged, so I will include that. When x was positive 1/2, the series diverged, so I don't include that. This is an open interval side. This is a parenthesis. This is a closed interval side. This is a bracket. Yes, it will matter. So it can converge on 1/2, diverge on the other. That happens a lot. The radius, there's a couple ways of thinking about radius here. My favorite way, the way that appeals most to me, because it helps you review a few things. What's the center of this series? If you center dot 0, good. How far from 0 is 1/2? How far is 1/2 from 0? If you center dot, oh, it's 1/2 away. Good. That's the radius. How far can I go and still make sure I converge? It's 1/2. The other way that's somewhat popular. One endpoint is 1/2. The other endpoint is negative 1/2. 1/2 minus negative 1/2 would be the diameter of the interval of convergence. The distance from here to here. Negative 1/2, 1/2 minus negative 1/2 is 1. That's the diameter. Diameter divided by 2 is the radius. Okay. Set the limit to be less than 1. Get rid of the n's in the limit. Solve the absolute value equation, inequality, sorry. Check the endpoints. If it diverges, open. If it converges, closed. Write it down, write the radius. If you have questions, you gotta come in, guys. It's kind of hard to figure it all out on your own, but you can do it. I believe in you with just these videos. I really do. But if you want questions, you gotta come in. Don't count on me being able to answer in like 5-second intervals in class. No pun intended. Okay, here we go. Limit. N going to infinity. X plus 1. Replace n with n plus 1. 2. Replace n with n plus 1. Reciprocal of the original. I want that to be less than 1. Oh man, my handwriting is awful. Now, one thing you notice when you cancel out everything, and this is suspicious, but it's cool, is you get x plus 1 over 2 with no more n's. With no n's. So I don't need to write the limit anymore. We just have that. X plus 1 over 2 less than, oh no, 1 bigger than negative 1. X plus 1, oh gosh, is less than 2. I multiplied everything by 2. And I'm subtracting everything by 1. I write that out because last year people got real worried about that stuff. Again, that's a potential interval. We're going to have to check the left endpoint. We're going to have to check the right endpoint. Don't just write this down. It's not right. It's very seldom will be right. Shrinky, shrinky, shrinky. Rewind it if you cannot see what happens next. Alright, here we go. Check. X equals negative 3. Negative 3 plus 1. Negative 2. Good. Over 2 to the n. These two simplify. He's going to slam the door. Sorry, everybody. Felix is rude. He slams the door when recording is going on. So, negative 2 to the n divided by 2 to the n. They're both to the n, so we can just divide them like so. This series diverges for 2 reasons. Can you tell me which 2 tests tell you it diverges? And again, if you said or thought the ratio test, you are very wrong. You are very wrong if you said or thought the ratio test. So, this series diverges by 3, 2, 1. Shout out to Gabe for coming in quietly. There you go. He's in the video again, guys. Felix, I don't know if I said Felix's name, did not come in quietly. It was Felix's fault, which I'm sure surprises none of you. Alright, this series diverges by the nth term test. As you take the limit, as n increases, it does not approach 1 value. The limit does not exist. The limit keeps slipping back and forth between 1 and negative 1. It also diverges by the geometric series test with r equal negative 1/2. The absolute value of r in this case would be equal to 1. The other version we'll check, the other endpoint we have to check was x equal positive 1. I have to peek over my hand. X equal positive 1. 1 plus 1, 2. 2 to the n divided by 2 to the n. If you said it without 1 to the end, that's actually what I wrote in the original recording. Joke's on me. It's the same thing. Okay? Now, 1 to the end actually helps you see something. You could say diverges by GST are equal 1. It also diverges by NTT. What's the limit as n goes to infinity? 1 to the million, 1. 1 to a million plus 1, 1. It's always 1. Its limit's not 0. So both endpoints diverge. Both endpoints diverge. Both diverged. Wow, it's getting ugly, huh? Sorry. So, the interval of convergence. Start by writing the endpoints in order. I don't know. I worry sometimes if I don't say in order. People write 1 comma -3 like it's a point. -3. When I plugged in -3, it diverged, so I used a parenthesis. Open. 1. It diverged. I use a parenthesis. Open. Okay? Converge. Closed. Diverge. Open. Radius. Oh, that was an ugly U. Alright, radius. What's the center of this series? This is why it's harder to think about this sometimes. If you said 1, you're wrong. It's always x minus the center. X minus the center. So what's being subtracted here? -1. How far from -1 to 1? How far from -1 to -3? 2. Again, the other method. 1 minus -3. 4. 4 divided by 2. Okay? You want to write that in the margin somewhere, because these all aren't equal, and it would make me upset, and I would take points off, and then people cry. But it's okay. Don't cry, children. It'll be alright. Just points. They're just things. You know, my least favorite line in that Superman movie is like, Man of Steel. It's like everyone dies in Metropolis, and the mom's like, oh, Clark, it's just things. But like, Mom, what about like the millions of people I killed fighting Zod in Metropolis? That's not good. No one wants that. Nathan's gonna slam the door. See, I told you guys. Now it's Nathan's fault. So, anyway, enough about Man of Steel. Here's where all the BC test kids start crying. Not BC test. You're all BC test kids. Here's where all the BC kids start crying. That's the slow way to do this whole problem. I'm getting rid of stuff on this page. I probably should have just deleted it. I don't care. So, the BC kids start crying when I say, that's the slow way. That we might call method 1. Would be to use the ratio test on this problem. Method 2, a much smarter way, the smarter way, the faster way, the better way, although I'm running out of room, I'm not going to write better, is to realize that this is what, Nathan?
A geometric series.
Now Nathan's in the video too. This is a geometric series. It requires that you realize this. It requires that you realize that this whole thing is both exponentiated to n. This can be written as one thing to the nth power. I rewrite 2 as like that. This will not always work. 1 is not a geometric series. Number 1 has n in the bottom. N is not something to the power of n. Okay? Okay. So what do we want? So GST you write this down, GST converge only when R is less than 1. I'm sorry. Oops. Absolute value of R. Come on, Leven. Step up your game. What's R here? R is the whole thing to the nth power. So you do this whole work again. It would be the same as we just did. Do it yourself. Make sure you understand. We would get... And we know... I'm writing this down for you visual people. For GST, we know diverge at endpoints. So, all in all, let's just move it all over here. So, all in all, I know you probably ran out of space. I don't know how you're printing it out, though. Diverges at endpoints, so IOC had to have been open -3, open 1, and the radius, sometimes they call it ROC, rock, is still 2. Okay? We don't need to check the endpoints to see the radius of convergence. Again, how far is 1 from the center of the series? It's too far. 2 units far. Again, some students last year preferred 1 minus -3. Find the diameter, divide that by 2. Radius of convergence. All right. So those are the 2 classical examples. Now the 2 interesting ones. Example 3. Oh, gosh. All right. Example 3. Let's set up this limit. Again, this is not a geometric series. Don't go looking for geometric series where they aren't. That has an n factorial. N factorial is no part of any geometric series I've ever seen. So we have to use ratio test. It's a ratio test problem. Almost everyone on your homework is going to be ratio test. But you want to look for the geometric series test ones so you don't have to check the end points. Limit. Set up the limit. Now, if you've done all the ratio test homework, I kind of doubt my BC kids will have by the time I'm giving them this lecture. You may have started to get good with this, where you can notice that if you set up the limit in the way it's going to cancel, things just happen nicely. N plus 1 factorial is going to be canceling out by n factorial. X to the n plus 1 is going to be canceling out with x to the n. So I can arrange my ratio like this, and I'm setting it equal to 1. And I'm setting it equal to 1. Oh my god. I told Saria to be quiet, and he ignored me. It's a great day. So, if you don't see how this ratio worked, if you don't see how the ratio worked, write it out the usual way, and then rewrite it this way. Okay, I'm telling Nathan to lock the door. That's why there was that awkward silence. So we don't have any more Sarias slamming the door. Not Gabe. Gabe is fine. I'm just tired of it slamming during my recording sessions. I know. Gabe wants another shout out. Okay. This video is getting long. Okay, anyway, it's going to cancel out quite nicely. Well, not so nicely. You'll see how the next one works. The next one's a thing of beauty. A grown man weeping with tears of joy. I'm pretty sure, based on my previous lectures, based on my knowledge of humanity, that's going to be a pretty quotable line. We want this limit to be less than 1. We need this limit to be less than 1. So, let's think about the values of x that will make this true. I'm talking about having 1 billion times x being less than 1. I'm talking about 100 billion times x being less than 1. I'm talking about 1 trillion times x being less than 1. I'm talking about the number of protons in the universe times x being less than 1. There's only one value of x that makes this true. That is a beautiful brace. Oh my gosh. Only true when, have you figured it out? X equals 0. Now, for those of you who have mastered the BC version of L'Hopital's rule, you might say, oh no, Mr. Leven, then it would be infinity times 0, which is indeterminate. To you I say, no. Infinity times 0 is only indeterminate when it's a really large number times a really small number. It's not indeterminate when all you're getting is 0. Because now, when n is 10, it's 11 times 0, 0. 1 million times 0, 0. 100,000 times 0, 0. That's less than 1 million. Oops. 100,000 million times 0, less than 0. And it just keeps being 0, so that's the only value of x for which this would be less than 1. Anyway, so that means the interval of convergence will only be x equals 0, because if x is at 0.1, it diverges. If x is 0.1, this limit's going to infinity. X isn't changing as n changes. X is a constant with respect to n. And the radius would be 0. How far can I go from 0 and still have it converge? No far. Nowhere. Okay, at least Gabe's laughing. An important point. Some people interpret this to mean, oh, no interval. Oh, no radius. No, a series, power series, series. I think series is the plural of series. Nathan, weigh in. Is series the plural of series?
Yes.
Power series always converge when at their center. Their center. And what's this guy's center? 0. So you always at least have one point of convergence. Now, 7 minutes, one more example. People are going to start pounding on this door. We got this, though. This example is so great. Hey, if you notice what's going on here, keep it to yourself for a second. Let's do the limit. N going toward infinity. Replace all the n's with n plus 1's in parentheses. What do I mean? 2 parentheses n plus 1. 2 parentheses n plus 1. Factorial. Reciprocal of the original, 2n factorial. Now, the more savvy among you might understand that that since we're in absolute value, these negative ones go away instantly. Others among you might notice that they go away as soon as I cancel them, because you should leave a negative 1. A negative 1 inside the parentheses, inside the absolute value does nothing. I'm just simplifying. I'm honestly sure that this is the series that's most likely to have students writing 2n plus 1 and 2n plus 1 here. Notice how it becomes 2n plus 2 because you have to distribute it. You have to distribute it, guys. All right, let's cancel. X to the 2n plus 2 is shorthand for x to the 2n times x squared. So this leaves x squared. How does this cancel? How does this cancel? These two factorials will cancel like this. And we still want it to be less than 1. How do I know that? Write this factorial out. 2n plus 2, 2n plus 1, then 2n, then 2n minus 1. This is probably David now. And they'll only start canceling after you get to this point, right? That cancels with that. That scribbles that out. I don't want you cleaning it up like that. Just, show me your work. Show me your work. Now, as n goes to infinity, the top is just one number. The top is just one number. The bottom is increasing. When n is like 1,000,000, the bottom is 4 trillion. And the top is just staying constant. So this whole side is going to 0. And how do we interpret 0 being less than 1 in this case? It would have been 0 for any value of x. So if it works for all values of x, how do we write that in interval notation? Don't write all reals here. That won't cut it in BC. Negative infinity, comma, infinity. And the radius of convergence, we say is infinite. So we say this series will always converge for any value. Now you can go as far as you want from the center, which is 0 in this case. You should be able to identify that. And let's just wrap it up. Which series is this? That's a hint. You should have realized it when you saw it. If you're getting good at this, if you memorize what I asked you to memorize, you need to be able to recognize that guy on sight. Nathan did it like 3 years ago. Nathan, what is it?
It's cosine.
It's cosine.
Cosine of x.
Nice. Nice save, Nathan. It's cosine of x. I didn't give him any hints, I swear. You guys won't ever know. But now that I said that, you all think I did. I'm just swiping it under the rug. But I didn't. All right. Nathan's pretty honest. You all know. All right. Cosine of x. So that series works for any values of x anywhere, as long as you use all of them, right? We can still find the Lagrange error bound, blah, 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 blah. Few last words, because I'm coming up close to the bell, as you can all see. This just summarizes what I was saying earlier. In the last unit, we found intervals for geometric series. It was not necessary to check endpoints. For geometric series, it's not necessary to check endpoints because geometric series diverge when r equals 1. However, the ratio test is inconclusive when the ratio is 1. Therefore, when using the ratio test, intervals of convergence, we need to check the endpoints. You have to listen to that bell. It's not even school for you, probably. Using one of the other tests. One of the other tests. All I want to say here is ratio test. Almost done. Won't work. Walk. Work. Don't use it. Here goes Rahul leaving. Again. Such a common mistake is people going back and saying, oh, and then I'll try the ratio test again at the endpoints. That will not work. It will be inconclusive. All right, guys. Make sure you do the homework for 8.5. Keep up the hard work. If you're not doing the homework, you're not working hard. You're not learning it. The videos are not helping. So do the homework. You have a lovely day. Talk to you soon. Bye-bye.